Greetings, this is Greg. I have made the case in the past that German aircraft engines were disadvantaged against their US and British counterparts by the relatively low-octane German aviation fuels. The octane numbers vary a bit, but most German piston engine fighters ran on either B4 fuel with about 87 octane or the better C3 fuel rated at 100 octane. The US fighters in Europe went into combat most often with either 130 or later 150 octane fuel, giving them a huge advantage. However, as with all things related to history and engineering, there is a lot of complexity to this subject and some room for disagreement. Much of this disagreement centers around the octane rating of the German fuels. Some say that they were equal to the US fuels, but had lower octane numbers only due to the differences in testing methods. That actually has some truth to it in a technical sense, but very little truth to it in a practical sense. This discussion is going to be a pretty long ride as there is a lot to cover, so get your preferred beverage, strap in, and let's get going. When we say octane in this context, we usually mean a fuel's octane rating, and that's the way I'll be using the term in this video. So what is the octane rating anyway? Well, it's a measurement of the fuel's ability to withstand detonation, also called knock, while under compression. With all other things equal, the higher the engine's compression, the more power it can make, up to the point where knock spoils the party. So just what is compression? For now, let's avoid getting into supercharged engines and just look at the mechanical compression ratio of a normally aspirated engine. This is the definition from Wikipedia. I'm not going to spend any real time on this because I cover compression in my Dora versus Mustang video. If you haven't seen that one or just don't want to watch it, just know that with everything else equal, a higher compression ratio will give you more power than a low one. In most cases, engine designers have to limit the compression ratio so as not to exceed the knock resistance of the available fuel. There are other factors that contribute to knock as well: cylinder head temperatures, combustion chamber design, valve materials, spark plug heat range, and a lot more. However, compression is the main factor when designing an engine to run on a fuel with a specific octane rating. One of the most important aircraft engineers working in the field of piston engines during World War II was a British man named Sir Harry Ricardo. He wrote a book called The High-Speed Internal Combustion Engine, which goes into tremendous detail on all aspects of aircraft engine design, really piston engines in general. He was also instrumental in the development of the sleeve valve engines and turbine engines in Britain. I don't think it's an exaggeration to say that his work probably directly influenced the design of every single aircraft engine used in World War II. One of the terms used in his book, and I'm using the 1941 edition here, there are several, but one of the terms is HUCR, which stands for Highest Useful Compression Ratio. This chart gives you a pretty good idea about how much octane will be required for a given compression ratio. It shows three different engine designs here. One is a sleeve valve engine, and for a given octane rating it can get away with the most compression for two reasons. First, the exhaust valves in a conventional poppet valve engine, like a Merlin or Allison, stay very hot and tend to promote detonation. Second, in this particular case, the sleeve valve test engine has the smallest bore here, and increased bore diameter can move an engine towards detonation. Here's another chart. This one shows 4 sleeve valve engines. All were as identical as it was possible to make them with the different bore sizes. Notice that as bore increases, the highest usable compression decreases. For reference, most World War II aero engines like the Merlin, DB601, Allison, and the R2800 Radial, these engines have bores from about 5.5 to about 6 inches. Back to our other chart. The E35 engine is the one that is most representative of a World War II aero engine. The E6 has a smaller bore and is more representative of an automotive engine. Notice that engine design has a significant effect on detonation. That's why there are three different lines here. Sleeve valve engines have the edge in this area, as do the smaller bore engines. However, regardless of engine design, the relative increase in HUCR with an increase in octane stays about the same. That's really important to understand. Thus, it doesn't really matter if we're talking about a Rolls-Royce Merlin with its 5.4-inch bore, or my Fiat 124 seen here at the drags with its 2.8-inch bore. The relative improvements we can get from increased octane are about the same. On the subject of octane, notice that Ricardo is using the motor method for the octane number. There were two common ways of rating octane back then, still today, the research method and the motor method. As a general rule, the research method is about 10% higher. So 100 octane on this chart would be about 110 octane via the research method. The number on the gas pumps in the United States is an average of the two. So if that 100 octane motor method gas was dispensed from a pump at a U.S. station, the number would be 105, although you'd be unlikely to find such fuel at your local filling station. The numbers on Ricardo's chart here represent upper limits in a lab with the technology of the time. The realities of the real world mean that in most cases designers went with compression that was a little bit lower. Back then, engines had less than perfect control of fuel delivery and ignition timing. They also usually lacked the super accurate sensors for air, oil, and coolant temperature. Thus, if an engine was set up right on the edge of the compression limit, it would eventually encounter a condition or a combination of conditions that would lead to knock. In other words, if the coolant temps were running a bit higher than normal with a mixture a bit leaner than normal on an engine that maybe had a little more carbon buildup in it than normal, it could lead to problems. So older engines had greater safety margins. Modern engines have all kinds of very accurate sensors monitoring all the engine parameters, and they're monitored by computers, and they have much more accurate control of the fuel and ignition. So modern engines get away with more compression. But the charts in Ricardo's book are a good representation of the limits of engines from the World War II era up through the 1960s, even into the 1980s in some cases. We've only scratched the surface of the book's contents on compression, and we have to move on. I did put the entire book in my Patreon section. Now, before we get into airplanes, I want to look at some automotive examples, because that will make it easier to get a good grasp on all of this. Let's take a look at some cars from 1969, all with comparable performance V8 engines of similar design. All are right around 350 cubic inches or 5.7 liters in displacement. Bore diameters are right around 4 inches. They're all 2-valve per cylinder and made from similar materials. In other words, all of these examples are similar but different engines that will have similar octane requirements. Actually, they all have the same octane requirements. Starting with the Ford Mustang. This car offered a performance version of the 351 Windsor engine, which had a compression ratio of 10.7 to 1. Plymouth had the Barracuda to compete with the Mustang, and in the Barracuda you could get a performance 340 cubic inch engine, which had 10.5 to 1 compression, very close to the Mustang's 10.7 to 1 ratio. American Motors offered a Javelin with a 10.2 to 1 343 cubic incher. That's the lowest compression of the cars being discussed in this group. Chevrolet had the Camaro to compete with the Mustang. They had a 350 cubic inch engine in multiple versions. The hot one had 10.25 to 1 compression. And Pontiac offered a performance 350 in the Firebird. This is not the same engine as the Chevy 350. The parts do not interchange. It's a different engine. They just happen to have the same displacement, which is confusing since they're both General Motors engines. Anyway, Pontiac's performance version of their 350 had 10.5 to 1 compression. So all of these engines are quite similar, not the same but similar. All had to run on the same types of gasoline, and all have compression from 10.2 to 1 to 10.7 to 1. In other words, in spite of the fact that there are some differences from engine to engine, they all have compression ratios within half a point of each other when configured by the manufacturers to run on fuel with the same octane rating. We can also look at the regular gas versions of these engines, in other words, the versions that did not require the higher octane premium fuel and ran the lower octane pump gas of the day, often called regular gas. In every case shown here, the regular gas versions run lower compression and less manifold pressure than their performance-oriented relatives. Chevy and Pontiac offered regular gas versions of their 350s, Ford offered a similar 351 in the Mustang, and Plymouth and AMC had regular gas versions of their engines, but also with lower displacement as compared with the performance variants. Now the regular gas versions all fall from 9.0 up to 9.5 to 1. Again, all within half a point when configured to run on fuel of the same octane rating. What I'm getting at here is that looking at an engine's compression ratio gives us a pretty good idea about the octane rating the designers were expecting to use. If you see a car from the 1960s that was built with a compression ratio of 12.5 to 1, and there were some, you can bet the designers were not planning on that being a daily driver running on regular pump gas. Conversely, if it had 9 to 1 compression, it was not going to require race fuel. It wasn't even going to require premium fuel at the pump. Now, comparing compression in World War II airplanes is a bit more complicated. For one thing, all the frontline World War II fighters were supercharged. That means they inhale and thus compress more air during the compression stroke than their normally aspirated counterparts. That has to be accounted for when comparing compression ratios. This complicates things, and it's more complicated than comparing the 60s American V8s we just looked at, but thankfully there is a pretty decent and reliable way to do it. We're going to need to calculate the supercharged engine's equivalent compression ratio, or ECR. This is going to be a bit controversial, as even that term is not agreed on. What I'll be calling equivalent compression ratio is often called effective compression ratio, or sometimes final compression ratio. I've seen other terms as well. Now, as far as I'm concerned, all these terms mean the same thing, although some people say that effective compression ratio is a term having to do exclusively with valve timing and not boost. So to be in harmony, let's say, with the largest number of sources possible, I'm using the term equivalent compression ratio, or ECR. I'm pulling this definition from Corky Bell's book on supercharging. The equivalent compression ratio represents the compression ratio of a normally aspirated engine that would be needed to achieve the same end gas temperature as a supercharged engine, where the end gas temperatures are the result of both heat from the supercharger and the compression ratio. I realize that definition probably didn't explain things very well. Corky's whole book kind of reads like this. It's a really good book, but it's a little tough to read, so I'll put it into my own words. As the temperature of the air in the cylinder during the compression stroke is a big factor in knock, the idea here is that if it's about the same in both types of engines, then both the supercharged and normally aspirated engines will be about the same distance from knock and require the same octane rating from the fuel to be used. There are various formulas for calculating this, and the one that is most often used is, in my opinion, dead wrong. It's so common, though, that I feel I have to go over it and explain why it's wrong. I very rarely feel the need to mention my own credentials. I generally don't use myself as a source, but this time I feel I have to do it. Not only am I a pilot and a former flight engineer, well, former flight engineer by profession, I guess technically I still have the rating, so I'm still a flight engineer. Also, I have a lot of time flying turbocharged piston engine aircraft. Additionally, I run a performance shop that deals almost exclusively with supercharged and turbocharged vehicles, and I've been doing it for a long time. I've read nearly all the NACA reports on supercharging. I used that information to write a book on supercharging. I wrote it over 15 years ago. It's available in ebook form on Amazon, but it's getting a little bit obsolete, especially the data in regards to centrifugals. I have put the book up in the Patreon section at no charge for the top tier members there. I also wrote the supercharging chapter in this book, although the editor changed the wording a bit from first to third person. But I guess my point is, I've been around supercharging and turbocharging for a while, and I know a decent amount on the subject. The formula I see most often for calculating ECR, which I think is incorrect, is this one. It's the boost pressure plus PSI plus atmospheric pressure, correction, it's the boost pressure in PSI plus atmospheric pressure divided by 14.7, then multiplied by the compression ratio. In other words, it's literally just the pressure ratio, like let's say 1.4 ATA or whatever, multiplied by the compression ratio. So at 14.7 pounds of boost, you have 2 atmospheres absolute, or 2 ATA, so you multiply 2 by your compression ratio, and you have your equivalent compression ratio according to this chart, which again I see all the time. When you think about this chart, initially it makes sense. If I'm running 14.7 pounds of boost, then I'm doubling the amount of air pressure. If I'm compressing all that air into the same space I was without boost, then it should generate twice the compression ratio, right? Well, that's wrong. And before I get into why it's wrong, let's just see if this formula even passes what I call a reasonableness check. Let's plug the formula into some actual cars and see if the numbers we get seem reasonable. Let's take a 2020 Mustang Shelby GT500 and plug in the formula. This car has 12 pounds of boost, so that's 1.82 atmospheres. Its compression ratio is 9.5 to 1, so we multiply 1.82 by 9.5 and get an equivalent compression ratio of 17.29 to 1. Does anyone know of a normally aspirated car that runs a 17.29 to 1 compression ratio on 91 octane pump gasoline? Of course not. So that formula utterly failed the reasonableness test. Note that the non-supercharged of the V8 version of the V8 Mustang, very similar engine, runs a 12 to 1 compression ratio, which is pretty typical of modern high-performance, normally aspirated cars. Now what about the Dodge Hellcat? It also has a 9.5 to 1 compression ratio and about 12 pounds of boost, so again that comes out to 17.29 to 1. Way too high to be realistic. If we run the numbers for this 2021 Camaro ZL1, also supercharged, we get 16.5 to 1, slightly lower than the other two, but still way too high for a normally aspirated engine. So why doesn't this formula work? There are a few reasons, but one is that it doesn't account for the density air change. The supercharger will heat up the air to some amount above ambient, even with a great intercooler. Note there are some intercoolers that can chill the air below ambient, but these use refrigerant or ice water for very short-term boosts of power. 99.9% of forced induction cars will have air temperatures in the intake manifold above ambient, whether they're intercooled or not. Now, it's the density of the air that matters, and in nearly all cases, doubling the pressure in the intake manifold gives something less than twice the air density, thus less than twice the compression. The formula simply doesn't work, and as we've already seen in examples from the Shelby, the Hellcat, and the ZL1, I could go on all day with example after example. This formula in question never works, although for some reason you see it posted almost everywhere you read about this subject. There is another formula that does work. It's almost the same, but you take the square root of the pressure ratio and multiply that by the engine's compression ratio. This isn't perfect, but it works very well. It's the formula I've been using for decades with success. Let's plug it into the GT500 and Hellcat and see what we get. We take the square root of 1.82, the pressure ratio, and we get 1.349. Multiply that by the compression ratio number of 9.5, and we get 12.8 to 1. Run the numbers for the Camaro ZL1, we also get 12.8 to 1. That is a reasonable number, as many normally aspirated, high-performance engines today have that much compression, sometimes a little bit more, a little bit over 13 to 1. This formula is also in harmony with the chart in Corky Bell's book. The formula I just explained itself is not in there, although he does point out that the other formula I talked about is incorrect, and he provides you this chart instead. So I feel I'm in pretty good company here if the formula I'm using is in harmony with Corky Bell. If you don't know who he is, he owns Bell Intercoolers and is considered a top-level expert on the subject of forced induction. So now we have a reasonable way to compare equivalent compression ratios on supercharged engines. That's going to be very helpful as we look at World War II airplanes and their octane requirements. Let's take a look at the 109E and Spitfire Mark I as used in the Battle of France. And I need to say, the last time I mentioned Spitfires in the Battle of France, I was flooded with comments saying the British never based Spitfires in France during that battle. I didn't say they were based there. I said they fought in the Battle of France. In fact, the British lost 67 Spitfires in the Battle of France, and we'll get to why that matters later within the context of this video. During the Battle of France, Spitfires were usually running 87 octane fuel and were limited to 6.5 pounds of boost. The German 109Es were running B4 fuel, which was also rated at the same 87 octane. So we have two airplanes running fuels with the same octane rating. These are two different engines, but are at least somewhat comparable as both are liquid-cooled V12 aircraft engines. Both are supercharged, neither have intercoolers. So let's compare the equivalent compression ratios. The Spitfire's all-out level manifold pressure limit for 5 minutes is 6.5 psi, which is 1.44 atmospheres, or ATA as the Germans call it. The Spitz Merlin engine has a very low compression ratio of only 6.0 to 1. So that gives it an equivalent compression ratio of 7.2 to 1. How does that compare to the 109's DB601? Well, the 601 doesn't have an all-out limit of 5 minutes, not in this version, but it has a 3-minute limit of 1.3 ATA, so I'll use that since it's the closest that I have to the Spitfire's 5-minute limit. We do the math and find that the 109 has an effective compression ratio of almost 7.9 to 1. So with both engines running their respective countries' 87 octane fuel, the 109 ran a bit higher effective compression ratio. Now, I think that that's because the Merlin was set up on the conservative side of things, at least partially because their carburetor didn't have the same level of precision in regards to air-fuel ratios and fuel delivery to the individual cylinders, as did the injection systems in use by the Germans. Of course, it could be that the German fuel just had more octane than the official number of 87. We need to look at more examples to get a better idea of just how good or bad Germany's B4 fuel was in regards to octane, and thankfully that's pretty easy to do. Let's add in an early FW190 running B4 fuel. Later, most air-cooled FW190s would use the better C3 stuff, but right now we're looking at B4 fuel, the stuff that's rated at 87. Now the 190A2 could run 1.32 ATA with its fuel-injected, air-cooled BMW radial engine on B4 fuel. It had a compression ratio of 6.5 to 1, which gives us an ECR of 7.47 to 1. That's not quite as much as the 109's DB601, but it's still higher than the Spitfire Mark I. Let's add in some U.S. engines. The U.S. did not have 87 octane fuel, they had 91 octane fuel. It wasn't used much for combat in Europe. It was used mostly for training missions and ferry flights, but we have engine limitations for it, so let's plug in those numbers. An Allison, as used in the P40, has a 6.65 to 1 compression ratio. On 91 octane fuel, it can run at 48 inches of manifold pressure, which is 1.57 atmospheres. That gives us an ECR of 8.33 to 1, the highest so far. That puts a big dent in the idea that the German fuel had octane far higher than its rating of 87, but let's look at some more engines running on US 91. One problem here is that we have to use non-intercooled engines and at or near sea level for this comparison to be at all apples to apples, or as apples to apples as is possible with this sort of thing. Most U.S. fighters had intercoolers, and most could run those high manifold pressures at very high altitudes. However, we do have some airplanes and engines that will work pretty well for this. We have the Wright R2600 twin cyclone engine. This was the engine that was slated to power the Grumman Hellcat before they upgraded it to the Pratt & Whitney R2800. I have another video where I talk about that. Anyway, the R2600 is very similar in specification to the BMW 801, surprisingly so. The Wright engine is only slightly larger, 2,603 cubic inches to the BMW's 2560. Both are 14-cylinder air-cooled radials with 2 valves per cylinder. In the B25, we have charts for this engine showing us the 5-minute manifold pressure limit on 91 octane fuel. It can run at 39.5 inches with a compression ratio of 6.9 to 1. That gives us an ECR of 7.93 to 1. One last example here, the Douglas C-54 runs the R2000 engine with a compression ratio of 6.5 to 1. That's a very common number in World War II era engines. Anyway, I've actually flown a DC-4. It can run 43.5 inches on 91 octane fuel, giving it an ECR of 7.84. I think it's very clear that the German B4 fuel was not vastly underrated in terms of octane. It certainly wasn't superior to US 91. From the data we have here, it appears to be quite similar or maybe very slightly inferior to US 91 in regards to anti-knock performance. Thus, our comparison of ECRs shows that it's probably somewhere between 87 and 91 octane. Now, let's take a look at U.S. wartime reports on German B4 fuel. The U.S. did testing of captured German fuel. One such test puts the B4's octane rating at 89, another at 91. So that's right in agreement with the equivalent compression ratio data we've come up with. So I'm very confident that that's reliable and it works. Not just because I've been using it for years, but because the numbers seem to work out here. I think that's a slam dunk, and we can determine that German B4 fuel was probably right between 87 and 91 octane, and that the planes ran ECRs close to or slightly lower than U.S. planes that were running on 91 octane, and they ran higher than the Spitfire when running on British 87. The Germans ran this B4 fuel in fighters right up until the end of the war. Examples of operational fighters that used B4 fuel almost exclusively include the FW-190 Dora 9, the TA-152, most 109G models excluding the G10, and some 109Ks. They also ran on B4 fuel in some cases. So there were a lot of German fighters using roughly 90 octane fuel fighting the U.S. and British fighters, which were using 150 octane fuel, which is an obvious disadvantage. Now don't worry, I'm going to get to Germany's higher octane C3 fuel pretty soon, but I want to stress the importance and resulting disadvantage of the B4 fuel. Again, it was in use from the Battle of Britain up until VE Day. In the mid-1930s, Shell Oil, which was the independently operated U.S. subsidiary of Royal Dutch Shell, developed 100-octane aviation fuel. The manager of aviation fuel for Shell Oil at the time was none other than Jimmy Doolittle, and he had to push hard to get this expensive fuel into production. It was an uphill battle for him because aircraft engines in the early and mid-1930s couldn't really take advantage of it. The project was often referred to as Doolittle's Folly. It was seen as a very expensive undertaking in an effort to produce a fuel which no engine required. Thankfully, Doolittle had the foresight to recognize the direction engine development was going and understood correctly that the high-octane fuel would soon be required. Across the Atlantic, the British had the foresight to start stockpiling and, to some extent, manufacturing this 100-octane fuel from various suppliers prior to the Battle of Britain. And by the time the battle started, most, if not all, British Spitfires and Hurricanes had been converted to run on 100-octane fuel. This must have been quite a surprise to the German 109 pilots. Spitfires over England had much more performance than Spitfires had during the Battle of France. There were actually two main reasons for this. The first was a large improvement in Spitfire propeller control, which I cover at length in another video. The other reason for the increase in performance was the increase from 6.5 pounds of boost up to 12 pounds of boost when using 100-octane fuel. Looking at this chart, we can see that the performance boost to the Spitfire from 100-octane fuel was tremendous. The increase in speed was about 30 miles per hour from sea level to about 11,000 feet. From there, the supercharger boost would drop off, but it would still have the edge over its 6.5 psi boosted counterpart, up to about 19,000 feet. I'm adding in an orange line for the 109E. These speeds are probably on the low side for a 109E because they're taken from a US test of a captured airplane running at 1.27 ATA, or just a hair below the plane's 3-minute limitation of 1.3. So again, probably slightly slow for a 109E, but not much. Now here's a yellow line for the 109 at its maximum 1-minute limitation of 1.4 ATA from a German test, presumably of a perfect factory new airplane. Keep in mind, it can only do this for 1 minute. The Spitfire can run that 12 psi limit for 5 minutes. It's clear that the Spitfire has the edge in speed with its 100-octane fuel, even when compared with the best numbers I can find for a 109E at its 1-minute limitation of 1.4 ATA. On 87-octane fuel, the Spitfire had about 1,000 horsepower. That wasn't bad considering its relatively small displacement engine. But the 109E had about 1,100. Now once the Spitfire got 100-octane fuel and 12 pounds of boost, power went up to 1,300, enough to give it a clear advantage over its German adversaries. Going into the Battle of Britain, Germans seriously underestimated the Spitfire because of their experiences flying against it in the Battle of France and from examining the wreckages, some of which were in decent condition. But the Spitfires and Hurricanes, people forget about the Hurricane, in the Battle of Britain had about 30% more power than they had in the Battle of France. It was the high-octane fuel developed in the United States and mostly supplied by the United States that enabled the Merlin to become at least equal, and in many cases, more than a match for the Daimler-Benz engines in the 109. So now that we have 100-octane fuel in the mix, let's look at the ECR numbers for it. The Merlin is now running an ECR number of 8.08, much higher than it was and higher than the 109E, although still not all that high for a 100-octane airplane. Let's look at some US airplanes on 100-octane. The Allison in the P-40 would run at 52 inches, giving it an ECR of 8.77 to 1. Of course, keep in mind the Allison has a primitive fuel injection system, so a little bit better fuel delivery than the Merlin in the early Spitfires. A P-40 with a Merlin and 100 octane, some P-40s had Merlins, would run 8.06, essentially the same as a Merlin in a Spitfire at 12 psi. We don't have too many non-intercooled US airplanes we can use for comparison. The PBY Catalina ran on 100 octane with 48 inches of manifold pressure. The R1830 Twin Wasp engine had 6.7 to 1 compression for an ECR of 8.49. The C-47 uses the same engine, has the same ECR number. Same with the Curtiss P-36 Hawk when it's running 100 octane fuel, which it usually didn't. Now, let's look at the German C-3 fuel, which was rated at 100 octane. Note there were changes to C-3 fuels during the war. I'll refer to them as early and late C-3 fuels, and I'll start with the early C-3 fuel. But before we do that, know that C-3 was a synthetic fuel made from coal. It was very expensive to make, and more than that, logistically challenging, because you can run oil through a pipeline to your plant that makes aviation fuel. Coal can't go through a pipeline. It has to go via train or much less ideally via truck. And it takes a lot of coal to do this, roughly 22 tons of coal per ton of fuel. The Germans had plenty of coal, that wasn't an issue. But making it into fuel was a big logistical problem, and it was very expensive, thus it was always in short supply. To close the gap with the Spitfire, Messerschmitt came out with the 109F model, which was essentially an all-new airframe, and it was a big improvement over the E model. The new 109F was in some cases powered by a new version of the Daimler-Benz V12, specifically the DB601N, and as in November. This is essentially a higher compression version of the older 601. Now instead of 6.9 to 1 compression, it has 7.9 to 1, which is a big jump. Maximum manifold pressure usually reported as 1.42 ATA. I have one reference for 1.53, but 1.42 is what's normally reported. There's also some debate about whether this was a 1-minute limitation or a 5-minute limitation in the 109F. As this video isn't specifically about 109 performance, I'm just going to skip that for now. Running on early C3 fuel at 1.42 ATA, the 601N had an ECR of 9.41, the highest we've seen so far. And that does indicate that the fuel's octane is probably a bit more than 100, or a bit more than US 100. Or maybe the German fuel injection system's giving it the edge. We really need to look at some other examples. The Ju-88 also ran on C3 fuel with its Junkers 211 engines. Data for the various versions of the 88 are a bit sketchy, but it appears that on C3 fuel it had 6.5 to 1 compression and ran 1.42 ATA. Finally, we have the FW190A3 and later A5s, which could run 1.42 ATA on C3 fuel for an ECR of 7.75 to 1, exactly the same as the Ju-88. That's considerably less than the US Twin Wasp Radial on US 100 octane fuel. Looking at the ECR data, the 109F is the standout here with its high compression engine when on C3 fuel. However, the 109Fs had a lot of problems with knock destroying the pistons, which is an indication that they were pushing the limits beyond what the fuel could support. If so, or rather even so, if we take the average ECR numbers across the range, it certainly looks like the early German C3 fuel was only slightly better than US 100. There are many Allied reports done on German fuel. B4 fuel tested very consistently between 89 to 91 octane, so slightly better than the German rating of 87. That makes a lot of sense, as the various US planes on 91 and the 109s are all within about a half of an ECR point of each other, just as we saw with the automotive examples earlier. The Spitfire lags behind, but I think that's because it's the only one using a float-type carburetor, and as I said earlier, I think it was being set up very conservatively. Reports on the early C3 fuel show it had about 110 octane via the US testing methods, although some US tests had it lower, as low as 99.7, but that was a test sample that had possibly been compromised due to weathering. Thus it could be that the 109F was pushing the limits a bit too much with the 601N, or it could be that the fuel's octane was inconsistent to the point that it was causing pistons to fail. This is a good time to mention Callum Douglas's book, seen here. I don't want to turn this video into a book report, nor do I want to summarize the book here. I don't think that would be fair. Mr. Douglas did a lot of very good research here, and his book is well worth the asking price. He's discussed some of the book's contents on YouTube, so I figure I can discuss those portions of the book as well without spilling the book's secrets. In regards to knock, he has several very interesting points. The first is about poor metallurgy promoting knock. The gist of it is that after Operation Torch, which was the Allied invasion of North Africa, Germany's supply of cobalt and other important metals dried up, and that it took the Germans over a year to get the resulting problems understood and under control. During that year, metallurgy problems were contributing significantly to knock. I don't really disagree with this idea, or for that matter, any of the key points in his book. Any disagreements I do have, and I need to stress this, are very minor, like the extent to which certain issues like metallurgy specifically, or octane levels, contributed to the lower than expected performance. I think that the fuel octane was the much bigger issue and that metallurgy was lower on the list. All of the examples of German engines I have presented so far predate Operation Torch, which took place in November of 1942. Thus, the engines I have presented so far were before the metal shortages reached their severe levels. From what we have so far, it looks to me like prior to Operation Torch, when using fuels of near equal octane, the German engines ran ECR numbers very close to the US engines. Let's move on. Daimler-Benz came out with the DB605, which was used in the 109G and later variants. Compared with the earlier 601, there were quite a few changes. The 605 had more displacement, 35.7 liters via 33.9 liters, via an increased bore diameter. They simplified certain things in the engine. For example, gone were the 601's beautiful roller bearings and the connecting rods. This makes sense, though. I'm sure it reduced cost and complexity, and I don't think the rollers were needed. Interestingly, the 605 has different compression ratios on each cylinder bank. One bank has 7.5 to 1, one has 7.3 to 1. According to Janes, another version intended to use C3 fuel had higher compression, 8.5 to 1 and 8.3 to 1. The problem is I can't find another source for this higher compression, 8.5 to 1 DB605. German tests usually don't mention compression ratios, so it's very hard to determine when and if this higher compression version was used, or even which 109 variants ran on C3. The 109G, which has all of them have the DB605, was the most produced variant of the 109, and it was the one most often tasked with fighting the U.S. Army Air Force. As far as I can tell, very few 109Gs ran on C3 fuel, and only then very late in the war. On 109s, you can see the type of fuel that they're using by looking at the yellow triangle on the left side of the fuselage. They usually say either 87 for B4 fuel, or they say C3. Every 109G I have seen that has the C3 fuel symbol on it is a 109 G10. The G10 was the final variant of the 109. It came out well after the G14, sometime around October of 44. The G10 uses the DB605 D series engine, which I don't think has the higher compression for reasons I'll explain in a moment. G10s are very hard to recognize. They were factory built. In some cases, they were older G models converted to G10s, so they're not all identical. The G10s can usually be recognized by the oil cooler scoop, which is different from earlier G models. Also, some G10s, including this one, not all of them though, but some, have this small blister forward of and below the exhaust stacks. That's related to the oil system. The 109K models used the DB605 D series engine and ran on C3 fuel without MW50. There was also a 109K variant that ran on B4 with MW50. However, both versions have the same compression ratio, and we know that because they can be converted from one version to the other very easily in the field. They didn't need to do an entire engine swap or change pistons to do this. It was basically just a question of adjustments and settings, valve positions, that sort of thing. So that tells me that the K4s on C3 fuel had been running the 7.5 to 1 setup, which means, at least most likely so, which means that I don't know if that 8.5 to 1 compression setup was ever used, but I can't determine that definitively. There was also a version of the K model with C3 and MW50. Not sure that ever saw action. If it did, it was in limited numbers. Maybe it had the higher compression ratio. which would make sense. And I should also say that I have seen some Allied reports of earlier G models with C3 fuel. However, I think every case that was actually a G10. In other words, a G10 crashes and the Allied officer inspecting the wreckage notices that it has a C3 fuel. He knows it's not a K model and reports it as a G8 or whatever. Every single picture I have found of a G model with C3 is of a G10. I'm not saying there were no G6s or G14s on C3, but if there were, they were exceedingly rare. Manifold pressure numbers for DB605s are also a bit of a quagmire to get into, but we're going to have to do it. First, we have versions that ran on B4 fuel. We have versions that ran on B4 plus methanol water injection, aka MW50, and then we have the 3C versions, and also, as I mentioned, some rare cases that ran C3 with MW50. To further complicate things, there was a period roughly 1 year in duration from mid-1942 before Operation Torch until late 1943 when manifold pressure limits were restricted due to reliability issues. This is the manual for a 109G2 from June of 1942, so well before Operation Torch. It lists maximum manifold pressure at 1.42 ATA. This is on B4 fuel. With the 7.5 to 1 compression ratio on the higher of the two cylinder banks, that gives us an ECR of 8.94, which is pretty high, higher than any 601 ran on B4 fuel, and almost as high as the 601N ran on C3. It seems to me that the Germans were pushing the limits of the B4 fuel pretty hard, even before metal shortages started becoming a problem. In fact, the Germans were restricting boost below 1.42 well before Operation Torch. This translated document shows that in June of 42, use of 1.42 was banned and 1.3 ATA effectively became the new emergency power limit. That limit stayed around again for about a year. Was this because of metal shortages or because they were just pushing the B4 fuel a bit too hard? I think it's a combination of both, but I think the latter is the bigger issue here. It really looks to me like somebody at Daimler-Benz was a bit too aggressive about raising the compression, and the metallurgy issue probably exacerbated it. I'm adding in 109G numbers here for 1.42 ATA and 1.3 ATA. Clearly, even without any metallurgy issues, the 109G at 1.42 was seriously pushing the limits of B4 fuel in regards to its anti-knock capabilities. Its ECR number is more than a half a point above the next closest engine on similar fuel, which is the Allison on 91 octane, and it's a full point above the average for engines on comparable fuels. So it seems very clear to me that the Germans were pushing the envelope here, and the result was piston damage, which is what you would expect if you don't have quite enough octane for the ECR numbers that you're running. So their fix for this, of course, as we mentioned, was to lower the maximum ATA for the DB605 to 1.3. Well, could the primary cause of this be metallurgy? I just don't think so for two big reasons. First, this reduction to 1.3 ATA was before Operation Torch. Second, and more importantly, the US and British engines didn't suffer from metal shortages to anywhere near the degree that the Germans did, yet they were running lower ECRs than the DB605, even when comparing the 605 at the reduced maximum of 1.3 ATA. By the way, for comparison purposes, it doesn't matter a whole lot which ECR formula you use. You can use the one that I said results in falsely high numbers if you want. No matter how you slice it, even at 1.3 ATA, the DB605 was running very high ECR numbers for fuel around 90 octane. So yes, the Germans had issues. They reduced manifold pressure because of them. I'm sure the quality of the metal in the valve material was a factor here, and it's probably a measurable factor. I have no doubt about that. The temperature of the exhaust valve is always a factor in knock, and different metals will be at different temperatures. but the fact remains that even with the inferior valve material, Germans on B4 fuel were running higher effective compression ratios than their Allied counterparts on equivalent fuel in non-intercooled engines. And the Allies didn't have metallurgy issues, at least not like the Germans did. Thus, it was just the fuel that was the larger limiting factor, and the Germans were pushing the B4 fuel too hard. Of course, higher octane fuel would be the answer, and there were improvements to C3 fuel which came on the scene around mid-1943. This improved C3 fuel is what we see used on the FW190A8 and the 109G10s and K4s. So let's start by looking at the 190. The FW190A8 can run a maximum of 1.65 ATA. That's really not all that much. It's not bad, it's just not really high. Interestingly, the 109K and the G10 are up really high. In fact, I suspect this is the highest ECR of any non-intercooled or non-water injected engine of the war. We also have data for a C3 variant of the FW190 Dora 9. I do not believe this version ever saw action, but if I'm reading the chart correctly, it ran at a maximum of 1.74 with a compression ratio of 6.5 to 1 for an ECR of 8.57 to 1. This Dora on C3 would not have been as powerful as the operational Dora, which ran B4 and MW50. So the C3 variant would have needed further development, probably the addition of MW50, to be worth the trouble. But it was a stopgap airplane, which is probably why they never bothered with the C3 and MW50 Dora 9, although it would have been pretty awesome. As a general rule, B4 fuel with MW50 was about equal or slightly superior to C3 without the MW50. At this point, I just can't say how good the C3 fuel really was, the late C3 fuel that is, in terms of knock protection. In some airplanes, like the 190A8, it doesn't seem to allow for any higher ECR than US 100 octane fuel did. Neither the BMW radials nor the Junkers inverted V12s run very high ECRs on C3 fuel. But there are the exceptions of the very late war 109G10s and K models, so those have to be considered. Their high ECRs could be because Daimler-Benz and or Messerschmitt knew that by this point in the war, the life expectancy of a German fighter was so short that the life of the pistons just didn't matter much. Or maybe they used a richer mixture than BMW or Junkers. Maybe the fuel varied in quality from one batch to another, and Daimler-Benz was betting on the higher side of the range and the others were being more conservative. I don't really know. We can look at some Allied tests on the late C3 fuel to get some more clarity on this. I'll start with this test, which covers German aviation fuels from the summer of 1940 up through late 1943. It's very thorough, and multiple samples were used in testing, and averages were taken and shown here. Notice there are essentially two types of C3 in this report labeled A and B. Type A was the earlier C3, essentially what was used in the DB601N high compression engine we discussed earlier. Type B is the later fuel. This report states that nearly all samples were from FW190s. That makes sense because in 1943, for the most part, 109Gs were running on B4 fuel, but essentially all 190s at that point were burning the C3. Notice that it shows a lean mixture octane rating of 96 to 97 and a rich rating of 125 to 130. That's a lot more than 100 or 110. So why the low ECR for the 190A8 and the experimental Dora 9? Let's back up for a moment. U.S. fuels typically had dual octane ratings, a lean rating and a rich rating. The lean rating mattered because it corresponded to the mixture typical U.S. planes would use with the mixture control in auto lean. This was used during cruise conditions when really high manifold pressure wasn't needed. Then there was auto rich. This provided a mixture ideal for knock limited power. In other words, it sprayed in a lot of fuel. This allowed more boost, or higher manifold pressure. The rich octane number would be relevant to a typical U.S. airplane in auto-rich. So the later German C3, as shown in this test, has a rich rating of 125 to 130. Well, that begs the question of why the FW190A8 with the BMW 801 did not take advantage of it. We know its ECR numbers are about the same as a typical U.S. radial on 100 octane. Thus, the Germans were using this fuel as about 100 octane. So what gives? Well, the answer is given in the same report, although it's an answer that raises further questions. Quote, aero engines used by the GAF are not being operated to take full advantage of the rich mixture potentialities of the C3 type of gasoline, rendering the reasons for the introduction and use of this fuel somewhat puzzling, unquote. In other words, the people writing this report don't understand why the Germans went through the trouble to create high-octane gasoline and then didn't exploit the fuel's octane rating. In other words, C3 at this point in the war had 125 octane, maybe 130, but it was being used at a relatively lean mixture, resulting in anti-knock protection equal to that of fuel of a lower octane, I would say right around 100. Let's look at another report. This one is from 1945, so this is the latest possible C3. And it pretty much echoes what we saw earlier. Earlier C3 had around 110 octane, and the later C3 had 125, maybe 130. This report also mentions that the German engines are not taking advantage of this, specifically because they're running maximum power at a relatively lean mixture. Let's take a super quick look at this NACA report. It's a report on the effect of mixture on knock, and it references Harry Ricardo's work specifically. This shows that the temperature of the exhaust valve has a large effect on knock, and that a rich mixture lowers the temperature of the exhaust valve. This is the main reason engines run rich mixtures to avoid knock. So, what's going on here? Why aren't the Germans running a rich enough mixture to crank up the manifold pressure? When looking at both BMW 801 and the UMO 213 on C3, the Germans were running effective compression ratios that were more suited to 100 octane than 125, and that's in agreement with what we see in the U.S. reports. It's interesting to point out that the Germans also rated C3 fuel at 100 octane and tested it using a leaner mixture than the Americans thought would be ideal. So, what's the reasoning for this? I have a few theories about it, one of which I think is very solid. Now, at first, I thought that the German C3 fuel might be very inconsistent, either due to production issues or contamination. Perhaps some batches would be 125 octane, some closer to 100, and there is some evidence to support that. Inconsistency is mentioned in some of the tests. And Callum Douglas discusses contamination caused by the fuel sitting for too long in certain types of aircraft fuel tanks, specifically some 109Fs, due to the fuel's tendency to break down the liner in the tank. That's a really interesting point. And I think it's a factor. But if inconsistency was indeed a big problem, then engine designers would have set up their engines to work with the worst case fuel. In other words, they would have set it up to run on 100 octane even if the fuel was 125. So this theory starts to make sense, but it falls apart under close examination because it doesn't explain the German tendency to run relatively lean mixtures. If the fuel was inconsistent in terms of octane, and it probably was to some extent, especially in regards to the fuel tank lining issue in the 109F, but if inconsistency was the main problem, then there would have been an even greater tendency for designers to want to run a rich mixture, and we know that generally speaking, they didn't do that. The same is true of the valve material. If the valve material is promoting knock, richening the mixture would help, but I don't see any evidence that they did that. The 190A8 ran a maximum of 1.65 ATA until the end of the war, and it really needed to run more, especially by mid-1944. I think the actual reason they didn't do that is related to something else Callum Douglas points out in his book, although not specifically in regards to this issue. He has evidence that the German C3 fuels didn't evaporate very quickly compared to other high-octane fuels. He also says that this caused the fuel to contaminate the engine oil, greatly shortening the life of the engine bearings. He does have a picture of some bearings, and while it's hard to be 100% certain of anything when looking at a grainy black and white photo, let alone then tying that to something else, I will say that what I can see in the photo that he shows is perfectly consistent with bearings damaged by diluted or incorrect engine oil. World War II aero engines had surprisingly loose clearances in terms of piston to cylinder wall, valve guide, and piston ring gaps. Thus, at very rich mixtures, some fuel would get into the engine oil because at these mixtures, not all the fuel in the combustion chamber burns. That's another discussion. Anyway, as long as the fuel that doesn't burn evaporates fast enough, it doesn't get a chance to build up and dilute the engine oil to any significant degree, and thus it doesn't cause a problem. In fact, many U.S. airplanes had built-in systems to allow the pilot to intentionally dilute the oil for starting in harsh winter conditions. Of course, they would limit the amount of fuel, and evaporation would do the rest. However, according to Mr. Douglas, C3 fuel doesn't evaporate well. Thus, more fuel would get into the oil, and once there would build up, dilute the oil, and become a problem. I think this is probably the reason the Germans ran ran lean mixtures. A richer mixture would have diluted the oil faster and shortened the bearing life, and thus the engine life even more. So I think this theory fits the facts I have pretty well. It's the best I have at the moment, if not totally solid. Let's compare the evaporation of C3 to some other fuels. Engineers call the rate of evaporation distillation, and it's expressed in terms of temperatures and percentages. We have good data on this for both German B4 and C3 fuels, and it's all in agreement with the stuff in Mr. Douglas's book. I don't have any period correct data for U.S. fuels during the war. However, I do have data on the current purple 145 octane fuel as used at the Reno air races. This is actually still in production and is reportedly essentially the same as US 150 octane used during the war. Automotive race fuels, and there are a lot of different kinds of automotive race fuels, and they always have this evaporation data published, as it's one of the primary considerations when selecting a type of racing gasoline. I would say it's the number 3 consideration behind octane and oxygenated versus non-oxygenated. At least it is in my shop. Professional tuners who use various types of race fuel consider this factor. So I'll include data for Sunoco SR18, which is arguably the best leaded race gas that's commonly available, depending of course on your application. Evaporation data is also important for fuels in modern airplanes, general aviation stuff, because it has an effect on hot versus cold starting procedures and a large effect on in-flight restarts at altitudes, especially in turbocharged airplanes. This is actually a pretty big deal in general aviation right now, because right now there is an ongoing search for a more environmentally friendly replacement for 100 low lead. And low lead is a big misnomer there. That stuff has a lot of lead. So they're trying to get a replacement for that not only won't cause knock, but will provide the same sort of characteristics for starts at high altitudes. Anyway, that's another story. So here's the chart I came up with. I wish I could have had data from World War II U.S. fuels. This is the best I can do. The chart is darn close. It isn't perfect because the published data for various fuels are published, the evaporation rates are published at different temperatures. Thus, some interpolation was needed, but the chart should be pretty darn close to reality. The curves for the Sunoco fuel is the only one that's off by much. Its curve is in reality much, much steeper than depicted past the 100-degree point. It goes from 50% to 90% in just a few degrees. That's this chart's only significant divergence from reality. So it's clear that C3 fuel does generally have a lower evaporation rate, especially at the oil temperatures World War II aero engines would be running. For example, a P-51 with a Merlin engine, maximum oil temperature of 90 degrees. This page is from the P-51B manual, which I have in the Patreon section. That's a pretty rare manual online, at least in its entirety. The later D models have the same limit. The Allison in the P-40 has a limit of 85 degrees. In the P-38, it's 95 degrees. The P-47 has a limit of 95 degrees, although, as with all these airplanes, there are some model-to-model variations. For example, some P-47s have an oil temperature limit of 100 degrees, but we're just trying to look at the overall big picture here. The German planes are a bit harder to get numbers for. Often the temperature limits are not listed in the manuals, so I found myself zooming in on pictures of gauges. It seems that nearly every German airplane I can find, including 109Fs, Gs, and Ks, all had limits of 85 degrees. Same with the air-cooled FW-190s. The 190 Doras had a higher limit on the gauge, about 120. However, it appears that the Dora is the only fighter mentioned in this video that displays its oil temperature leaving the engine instead of leaving the oil cooler. Thus, its temps are really about the same as the other German airplanes. At least as far as I can tell, there's some real gaps in some of this data, but I'm doing the best I can with it. Now, back to our chart. I'll add in the oil temp limits, and you can see the U.S. planes generally run slightly higher oil temperatures, which will help evaporate the fuel out of the oil. Of course, the oil will be hotter when it's in the engine. And remember, all of these except for the Dora have numbers for the limits after it's gone through the cooler before it goes into the engine. At these temperatures, oil is going to be exiting the engine at 105 or maybe up to 120 for the hotter U.S. engines. Looking at the evaporation curves, you can see that in that range, the C3 fuel has fallen well behind in its ability to evaporate. Keep in mind that the oil temperature is important for getting the fuel out of the oil, but what about keeping it out in the first place? Well, higher temperatures of the cylinder head are going to be a big factor there, and again, the U.S. engines come out ahead. For example, the air-cooled P-47's engine had a cylinder head temperature of 260 degrees, a maximum temperature of 260, versus a max temp of only 220 for the FW-190. We can't look at cylinder head temperatures for the liquid-cooled engines, but we can look at the coolant temperatures, and again, the U.S. engines run with higher limits. A maximum coolant temperature for a P-51 is 121 degrees, a P-38 125. Again, it's a bit harder to get numbers for the German planes, but it looks like all the 109s had a maximum coolant temp of about 100 degrees. So after combustion, any excess fuel, and there would be excess fuel when you're running a really rich mixture, was going to be less likely to evaporate than it would be in the U.S. engines, and thus would be getting into the oil. Back to octane. So yes, in the later part of the war, C3 fuel did have 125 octane, sometimes even 130 when used on a test engine in a lab. However, in practical terms, that was meaningless in the FW-190, the A model that is. I think the reason has to do with the evaporation rate of the C3 fuel and the low maximum operating temperatures of the German engines. But even if I'm wrong about that, for whatever reason, C3 fuel, as it was actually used in the 190A models, had anti-knock properties that were probably very close to the German rating of 100 octane, and in all cases, with the exception of the usage in very late 109s, and even then only in some of them. Throughout most of the war, 109s were running B4 fuel. Everyone wants to talk about 109s on C3, but the reality is that most versions ran on B4, some on B4 with MW50, but the US had P-47s running 150 octane fuel with their own version of MW50. So the US and the British had a huge advantage in fuel octane from the Battle of Britain on. What about the very late war 109 G10s and K4s running on C3? At 1.8 ATA, they had a very high ECR of 10.6 to 1, which is quite high. So at least in some cases, it looks like C3 fuel was used as a high-octane fuel. But those cases are rare and seem to be isolated to a very small number of airplanes. The Germans seemed pretty desperate by that point in the war. Well, they were pretty desperate by that point of the war, and the life expectancy of a new 109 was so short, I'm not sure they were too concerned about engine bearing life at that stage of the game. So maybe they just richened up the mixture and accepted the decreased bearing life. Or maybe they didn't and just figured that the pistons wouldn't wear through from detonation before the plane was destroyed anyway. What I can say is that all the evidence shows that the German aero engine performance was seriously hampered by low-octane fuel throughout the war. B4 fuel had about 90 octane and it was used right up until the end of the war. In the case of C3 fuel, sure, it had high octane numbers in lab testing, but in the reality of usage, in the most common applications, it didn't. The planes running C3 for the most part operated as if they had around 100 octane. This includes all the FW190A models from the A3 to the A8. It's also true of the Junkers-powered airplanes on C3, like the Ju-88 and the experimental Dora we talked about. The early 109Fs with the DB601N ran higher ECRs as if they had a bit more than 100 octane, maybe 110, but they burned up pistons at an alarming rate, and the 109F engines were changed to DB601Es that ran on B4 fuel. So relatively few 109Fs ran on C3. The G10 and K4, when run on C3, did run high ECRs, but probably sacrificed engine life to do it. At that point in the war, it didn't matter. Either way, these are the only German planes to use C3 as if it had 120 to 130 octane, and they represent a very small percentage of the Luftwaffe. All these other things we talked about are undoubtedly factors in knock. Certainly, metallurgy was. I don't think Callum Douglas is wrong about that. I just think it's a little bit of a smaller factor than I think he attributes to it. The lack of intercooling on German engines was certainly a big factor. All high-altitude U.S. fighters and all Spitfires from the Mark 9 on had intercoolers. The 109 never got an intercooler in a production variant. Neither did the FW190. The TA-152 did. Too little, too late. Again, the TA-152 ran on B4 fuel, so it had about 90 octane versus the U.S. fighters running 150. Exactly what hampered the German engines and to what extent is a bit tough to quantify. Well, certainly it's tough to quantify the extent to which these things hampered performance, but I think the lack of high-octane fuel that was usable as a high-octane fuel has to be the number one issue. After that, I would put the lack of two-stage supercharging until very late in the war, then the lack of intercooling again until very late in the war, and somewhere after that, the metal shortages. In fact, now that I think about it, it could be argued that the lack of two-stage supercharging and intercooling should be at the top of that list, because the TA-152 was competitive with the latest Allied fighters and superior at very high altitudes, and that's on B4 fuel. Then again, if they could have used 150 octane in that airplane, it would have been even better. I have a video on the TA-152, and I cover it in a pretty large degree of detail. Before I go on, I want to mention Chris, aka Bismarck, at Military Aviation History. I assume anyone watching this channel is already familiar with his channel. If not, you really need to check it out. Chris is crowdfunding a book on the Stuka dive bomber, along with Bernard of Military History Visualized, another well-researched channel. I'm excited about this book, not only because the Stuka is an interesting airplane, and dive bombers in general are interesting, and the Stuka is maybe the most interesting dive bomber, but also because Chris is digging through the German archives to come up with some primary source material that few people have ever seen. I think we're going to get a better look into the plane and its operational use than we've ever had before. His crowdfunding is going pretty well, but the more he gets, the more he can include in the book via something called stretch goals. This is all explained on his page. I'll link that in the description, so I'm asking you to click on that link and take a look there and consider buying that book. Getting data from the German archives is not as easy as just showing up and asking a librarian to make photocopies for you. It's very time-consuming and it's a costly process, and very few people are doing it. Not only that, very few people can do it. Chris is German, so he can navigate the bureaucracy there. He speaks German, so that's a big factor. He also speaks English very well, but more important than that, he understands aviation and speaks aviation English and aviation German, and that's important when doing this kind of research. Aviation has a lot of specific terminology, and just being a native German speaker doesn't mean that that person is suited for this type of research. I'm hoping this project goes well enough for him that not only the book works out well for him, but I'm hoping he's incentivized to keep digging through the archives and putting out new information. That should help close up some of the gaps in the information out there on German World War II aircraft. For example, gaps that cause problems in this video. I was not able to determine which planes, if any, with the DB605 ran that higher 8.5 to 1 compression ratio. That information just isn't out there in the public domain, and if it is, I couldn't find it, and I tried really hard. I actually looked at Stukas a bit for this video. Here's a performance chart from the manual. It has some great information, but try and find the compression ratio for all the various UMO 211s. I had to just assume they're all the same, but I'm not certain of that. It's not given in the pilot's manual, although it does have the fuel and the ATA, which is pretty nice. So that's all for now. Thanks to all of my subscribers. I appreciate each and every one of you. I try to answer all of your questions. Sometimes it's a little tough when the video first comes out because the questions all tend to stack into the first few days of a video's release. Thanks to all of my Patreons. You folks really make this channel possible. I have added some stuff to the Patreon section with the release of this video, including Harry Ricardo's book, which I think is fascinating reading. If you're interested in piston engines, it's almost a must-read, especially if you plan on becoming an engineer or going into that sort of a field. I added my book on supercharging as well, and of course you can find the aircraft manuals referenced in this video, the 109G2 and so forth, as well as the P-51B in the Patreon section, and a whole lot more. So goodbye and have a great day.